checking that. That's fine. That's working. That's working. Cool. Right. We're ready, I think. So, yeah, last one. You guys have made the cut. That's why we've got the group this size now. that's the special part about it. So, as you all know, there's not going to be any Proteus in this one because we've covered basically everything that we needed to. Last week we went through all of the ordering process and the Gerber's generation and all that, and even through JLC. So I'm going to focus on the actual board itself. Purple board. I did go for
A lot of respect for that. A lot of respect.
So it actually looks quite nice. I like the purple silkscreen. So what I'm going to do is go through all of the errors that I made on the board initially. So you'll see yourselves what to watch out for. There's a couple of... You what?
It's going to be a short session.
Yeah, well, it's actually... There's about 20 slides on this one. So you'll... Yeah. And then I'm going to do a bit of a demo. So I'll show you how to essentially use like an off-the-shelf sound card to do some fast Fourier transform analysis and that kind of stuff. But it's a lot easier to understand when you've got a visual of it. So whilst I'm doing it, you'll see what the sound card's doing on the scope as well, so you can get a feel for exactly what's happening. And then, yeah, questions. I'll put the thermal runaway thing as an extra, so that's the phenomena that I'll be talking about. But by that time, the time of the lecture might have gone on for a bit too long. So if we've got time and you're interested, I can demonstrate thermal runaway as well. So that's their pictures of the board, which are looking pretty nice. So essentially, got them produced, posted, and started building. So errors. So this one's pretty obvious, right? Yes, but the reason being is, let me get the pointer. Here. So I didn't, the silk screen for the 3.5mm jack, you know that we use the pickaxe part out of the Proteus libraries, not quite accurate. So you need to watch out for using default components out of the Proteus library, might not be accurate. So this part needs the silk screen extending, then I wouldn't have placed this too close to this connector here. Next one. Can anyone guess what's wrong with that? No. I'll give you a hint. This gap here.
Oh, if you mounted it.
Yeah.
It's too far back.
Yeah. Yeah. So you might catch the odd, like a slight thread of the potentiometer, but you want it against the chassis that you're putting it in, essentially. Now, this one again is another silk screen, so it's just fractionally too small, this one. But if you're being picky about it, then you'd want that silk screen a little bit bigger. This is an interesting one. That's a diode. Putting a dot on a diode, a fiducial mark, is ambiguous. Have you put the dot on the cathode or have you put it on the anode? The silk screen doesn't tell you that. So you don't want to do that for diodes. So avoid ambiguous marks, and then you want to actually use these kind of marks for diodes. K stands for kathodos, which is what it came from, the word cathode. It's a Greek word. The reason why it's marked with K is because otherwise it get confused with C capacitors. So, but notice they've got a dot on the ambiguous one as well. So yeah, and this is clear as well. This one, that would be your cathode side. So something to watch out for. So we've got an actual picture of the board and then the silk, the layout here. D1, the silk screen has been chopped a little bit because the silk screen on this, on the design is too close to the cathode. Want to avoid that. Also, the fiducial shouldn't be there for the diode, but it is, and it's merged into the lettering of R as well. So this is the kind of stuff that you need to watch out for when you've got small features on your silk screen. It's a bit It's a bit inaccurate. Okay, more serious issues. So I've put components on the bottom and top of this board, okay? And I've also put through-hole components on the top of the board and the bottom of the board. Now, what I did was these through-hole components are the diodes that live on the top of the board. We're looking at the bottom, and they completely clash. The legs are trying to go through some surface mount components on the bottom side. So you need to watch out for the fact that, you know, don't put through-hole components where there's going to be something on the underside. There's another more serious problem. It says these pads are shorted on the tab. The reason for that is that the TO263 package out of the Proteus libraries that I told you to use isn't fit for purpose for the D squared pack, the D2 pack package for those linear regulators. So don't use it. If you've made it already, delete the D2 pack package out of your library because it doesn't fit. What you want to do is just go into the datasheet of the linear regs and just build that package footprint from scratch because it's easy. It's just like 3 squares. So it's an easy one to do. But the problem is that underneath this linear reg, there's a big metal tab underneath it for heat sinking purposes mainly. And the metal tab came out and across under here a bit. And then if you think where those diodes are going through the board, the tiny little solder bump underneath then shorted to the back end of that package. That's what happened. Silkscreen is in the pads of these as well. So that's the one I just simply missed. You've got C4, C3, and C5 are in the pads of there. They didn't get printed by JLC. And another thing, it's easy to miss, the mounting holes in the corners. This is just about okay, but it really should have had a bit more clearance. You should put a marking on the PCB for, if you're using a hex standoff, take the widest diameter from edge to edge of the hex and put a mark on the PCB so you know you can keep out of that region. And then the power LED is a little bit dim, I found, so I'm going to reduce the resistance a little bit. Make build notes when you build your first PCB, well, any PCB. If you create a list as you're going along, you're not going to forget anything, and it's important to do it as you're going along because otherwise you will forget. Cool, right, so that's all the layout stuff. So I've got 2 effects of the circuit that really could have been, that will need to be addressed. The first one, you might be able to intuit this. If you've got this circuit on and you've got headphones plugged in, and then you take the jumper off J3 to move it to a different mode of operation, what's going to happen? Yes. It's a bit worse than that, but yeah, it'll fully saturate on a rail because you've removed the feedback loop entirely. The op-amp just doesn't have a clue what to do, and you'll hit a rail. And when you've got an amplifier like this that's got capable of outputting quite a lot of current, and you're feeding it 12 volts, you know, you can seriously damage headphones by doing that. So if you're using it in its current form, make sure that you turn it off before you start messing around with the jumpers, and then you can turn it back on again. A couple of things that you can do though. You could put, I've not tested this, so don't quote me on it, but you could put a large resistor in the feedback loop permanently, which will always maintain a DC feedback, you know, path, even when you remove the jumper. That'll create a massive amount of gain, but we don't care, the DC will hold. The other thing that you can do is put output capacitors on the headphone, you know, after the transistors. The output capacitors will stop the DC getting through. What else could you do? Or you could implement something called a DC servo. If you want to find what that is, Google it. But essentially, it's an integrator that will constantly measure the output of the system and then integrate through, and it will remove any offset entirely. But it's quite a bit more complicated to implement that. The second thing is this thermal runaway issue. So bias transistors can undergo thermal runaway. So what happens is, as a transistor gets hot, as a PN junction gets hot, the forward voltage goes down, doesn't it? I spoke about it yesterday. So the forward voltage of a diode drops. So it might start at 0.6 volts, but as you go to 100 degrees, 0.5, 0.4, 0.3, it drops. Problem with that is that we're using the forward voltage of this diode to bias the base of this transistor, for example. If the forward voltage across this junction drops and this doesn't, then the transistor is going to get driven on harder and harder and harder. That's what's going to happen. And when that does happen, the transistor gets hotter and hotter. It's a positive feedback loop that can eventually cause the complete destruction of the output devices. And I've had to replace them on mine because I did completely destruct mine. So, D3 and D4 can mitigate this problem, but only if they're thermally bonded to the transistors. Because then, as the transistor gets hot, D3 gets hot, and the voltages track each other. You stop that mechanism from happening. Mine are not thermally bonded in the slightest. They're just completely separate from each other. So, yeah. I'll show you. Yeah. There's a number of ways you can do it. You can mount them on the same heatsink. You can use larger devices that don't heat up so rapidly, because I've got tiny little transistors that will just the heat generated. They can't dissipate it very well. But if you've got the diodes and the transistors mounted to a heatsink or plane that are properly connected together, then the issue starts to decrease. But I had to do something on mine to fix that. This is a bit of technical stuff. So if you are interested in reading more about this phenomena, when you get the slides, you can check these links out and understand the circuit a bit more. But very, very briefly, when you connect the collector and the base of a completely the same model of transistor that you're using for the output, you turn that transistor into a diode. That's all it becomes. Can you imagine that? You've got this diode junction here. When you connect these two together, you've got one terminal in, one terminal out. It's just a diode. The good thing about this is the diode here is the same type and the same everything as the diode here. So then if you can thermally bond those two devices together, you haven't even got diode to transistor differences. You've just got the same device. The second thing is this thing called emitter degeneration. This emitter degeneration resistor. Without going into detail, that causes a little bit of negative feedback, limits the gain of the amplifier a little bit, but in doing so, it improves the linearity, so less harmonic distortion, and improves the temperature stability. I've taken a picture from the Bible, which is the Art of Electronics, on this. So again, if you want to read it after, when you've got the slides, it's quite an interesting article. This is what I did to fix mine. So lifted them off, put them on the thing, like on the output transistors, and covered them in thermal goop. And then, surprisingly enough, that stops the thermal runaway situation from happening. So at least I knew I was on the right track. Cool, right, so we are going to do a little bit of demo stuff. So I'm going to show you the measurement setup, do some loopback tests. So that means I'm going to test the sound card alone. And then we're going to go through a bunch of amplifier tests to actually measure this device as well. Now to do that, I'm going to close that. And I'm going to, there we go. So hopefully, I don't know why it does this. You have to press the zoom button twice. But now it should stay. So you can see the setup. So you can see the sound card. It will focus. You see the oscilloscope. And for the loopback test, all I've got is the sound card connected from the headphone output to the microphone input. I've got this as a T piece because I'm simply measuring it with an oscilloscope as well, so you can see what's going on. So what I'm going to do is run a frequency response. Couple of things. It's kind of flashy and stuff because the laptop is dying doing this. I'm recording audio screen, and it's trying to do fast Fourier transforms at a fast rate as well, so don't worry about that. The second thing is that you can see all this kind of like noise and stuff. That is, again, artifact of the measurement system because I'm running it fast, because you don't want to, if I was doing this properly, then you'd run this sweep over a long period of time rather than, you know, letting it go quickly. But you'll see that as the peak comes along, it'll get rid of most of those. And then you can see, obviously, the time series and the frequency series situation at the same time. Again, this roll off at the low end is because of the speed at which I'm doing this test. So what I'm going to do is I'm going to load the system up first. It's important to do your tests under the same conditions that you are expecting to use it. And the amplifiers have a nice and easy job when you haven't loaded them with anything, and then all of a sudden they have to do some hard work, and then things fall apart. So, obviously you can hear that. Can you see that the amplitude has dropped slightly? I'm also going to remove the power going to the oscilloscope. Oh, sorry, the oscilloscope's unplugged now, so that's not going to be showing you. So all I'm going to do is clear the peak hold. I'm going to let it do one more sweep, and then I'm going to save this as a reference waveform, because this is the loopback testing. This is telling us how well the sound card is doing on its own with nothing else connected. So we just have to bear with a second, and I'll record it. I'll just let it sweep over those little bits because it'll get rid of most of them.
So this is like our baseline sound.
It is. So this is the baseline of the first type of test, which is a frequency response. This tells you how flat this is. The flatter this is, the better. Meaning that at certain frequencies, it amplifies the audio at exactly the same amplitude.
So it's showing the sound card's pretty damn good.
Exactly. The sound card is actually fantastic. It really is. And like I say, the bottom end is flat. It's just the artifact of the speed at which I'm doing this test.
Yeah.
So I'm going to let that go. There you go. Most of those are gone. I'm going to save this waveform, like so. Save the peak hold data, and then stop that. The second reference test that I want to do is the THD plus N, which is a 1 kilohertz signal. You're going to get really bored of that noise, by the way. Can you see it picks up my voice?
Yeah.
Can you guess how that's getting into the system?
Is it because it's recording this session, and so there's a DC? Well, I was going to say within the computer.
No.
No.
It's nothing to do with anything else apart from the test gear that I've got on my bench.
Then there's just interference.
No. No. It's nothing. It's real. It's not like a noise or an extra distortion.
Vibration.
Is
Yeah.
it the headphones are picking up
Yeah.
your voice?
Yeah.
And so therefore, although they're being driven, they're
Yeah.
also pushing back?
Yeah. So you can get a feel for how sensitive these measurements are. I'm talking to you guys. The headphones they're not even microphones. You know what I mean? That's not a microphone. But you can hear it's taking up a voice. So I have to kind of get rid of that.
I was going to say, so could you change the tone? Well, I guess.
But this is a mic input, isn't it? It's got huge gain.
I'm going to move over here so that it's not going to... yes, the gain's quite large, but I've reduced the gain because the output of the headphone amp is going into the headphones at maximum level. So if it was really high, super high gain, I'd be clipping. The reason why you can see it, I'm just going to have to put up with that. It's actually not really there,
Yeah.
is what it is. The reason why it's there is because it's a minute level. It's absolutely tiny, that level.
Pico and nano.
It's so small, yeah, it's
Yeah.
fractional voltages. So that's what these things can pick up. If I put this on the oscilloscope, and I will do once I can connect up my amp, you can see this on the oscilloscope. Can't see that. Can't see any of those either. You know what I mean?
So if each one of us came and spoke near your headphones, I guess that peak would be in a different place because we've all got different, like, our tone's different. Like, Ellen and Cookie got a slightly higher tone. I could produce a higher tone. Like, if we were to change, that would then show somewhere else.
Absolutely.
Yeah.
You'd see the spectral.
It wasn't. Sorry, Gavin. Yeah. Just an observation.
Yeah, you would. You'd absolutely see the spectral content change.
After a night out, it'd be a lot better.
Yeah.
So course after singing at night.
Exactly. So what I'm going to do now is I'm going to connect my. I'll show you actually. I'm going to connect the actual headphone amplifier in. So what I'm going to do is go from. It takes a bit of faffing around. The headphone output of the sound card goes to the the audio input on my amplifier. And then the output of my amp goes to the microphone input of the sound card. So just instead of it being a complete loop back, it's now just it's got my amp in the in the path. So I'm going to power it, and I'm going to put an oscilloscope back on now because I've got these wires hanging off it. I can do the rest of these tests, and you can see what's going on. Remind me though to take the scope off when we're doing the last FFT test because the noise on the ground lead can interfere with it slightly because I might forget. Right, so now the amplifier, remember we've got those jumpers to change it in all the different modes. The amplifier now is in class B. So it's in crappy mode. Basic mode, that's better. And it's also uncompensated. So you can move the feedback loop and compensate for the output transistors. It's not, it's just op amp, class B, straight out.
Question.
Yeah.
So I'm just a bit confused.
Yes.
This one.
Yes.
Where does it come from?
Where does it come from?
Yeah.
This graph is exactly the same information as the oscilloscope waveform.
Yeah, where did you get that?
The sound card, I see what you mean. The sound card is generating that sine wave. This software, let me show you. See this?
Yes.
This is a signal generator widget.
So this is a software for the card?
No, this is actual software that you can download and it works with any sound card. So this software called Spectra Plus Sound Card Edition is actually really good. It's really good for doing this kind of analysis. So the software generates a perfect sine wave with no harmonic content whatsoever. And then it plays it through the headphone output, just like you hear, just like a music, apart from it's just a perfect sine wave. Is that?
Yeah. So where do we have this? Generates this perfect sine?
Yeah, because a perfect sine wave, what do you think a perfect sine wave would look like on this? Yeah, exactly. So it's generated a perfect sine wave.
This is a measurement.
Yeah, in software. So the software sine wave would be perfect. It's then had to go through a digital to analog converter. It's had to go through an output stage. It's had to go through a wire, and then it's had to get resampled back in. Yeah? So the loop back is just testing the sound card. The testing that I'm doing now is the sound card and my circuit. Yeah? Perfect. Perfecto. Right. Now I'm going to, what am I going to do? I'm going to take that off. And we're going to have a quick look at, so okay, just a quick one whilst this is on. Ignore this, my voice. What I didn't do, I'm just going to quickly, 2 seconds. I'm going to quickly pull up the THD plus M measurement. So I can click this button here, and then that will bring it onto the other screen, obviously. But there you go. This tells you the total. You see that? I can't talk. But this tells you the THD plus N content. So what I'm going to do is I'm going to turn ultimate. I'm going to turn infinite averaging on, and then I'm going to be quiet for a second. going to stop there. So I'm going to write that down. So we've got 0.0015% THD. That's the measurement. That's because the software, what it does, you know that notch filter thing that I went through? It takes a measurement, notches out the fundamental, measures what's left. That's what this is doing for us. So that's our benchmark THD measurement. Cool, right, so now I'm going to reconnect the Class B amp.
Okay, another question.
Yeah.
Sorry. Then what was the point of recording
Frequency response.
the line that you wanted it to be smooth?
Yeah, so these are two different tests. The first test tells you how, for each frequency that you put in, so throughout the whole audio range, is your amplifier going to amplify each frequency the same? If it isn't, like when you've got like an audio thing and you can bass boost or bass reduce, if you do a bass boost, for example, you'd see that line was high and then came down. Or if you bass reduce, the line would be low, then upper high. So that as you know, that swept the frequency up and down the entire spectrum to get that line at the top. Whereas this is analysing one frequency very carefully. So that's why I put lots of averaging on and really reduce the noise floor so that we can pick out the harmonic content which amplifiers can create. It's a different type of distortion. The reason is because transistors might amplify a voltage slightly differently than another voltage. So if you feed 0.0014 or 0.0015 volts, they're bad numbers to choose, 1 point whatever, the amplifier might change its gain slightly, and that's what causes harmonic distortion. So essentially they're two different tests. Yeah?
You didn't look at the face, so I assume because it's such a short phase.
I have not figured out how to look at phase changes on this yet. There might be a way, but I've not.
Is that what causes harmonic distortion?
Yeah.
Imperfection in silicon,
Is it imperfection in silicon? I don't know what the root cause is. I don't know what the root...
It's basically transistors that behave in not uniformly.
Yeah. Because transistors, you've got the linear range, where if you're not right at its top end or its bottom end, it's meant to behave linearly.
Yeah.
But even during that linear range, it's not perfectly linear. Yeah. And you get these... But do you know, these levels are so low, you can't hear that at all. But what you can hear is a Class B.
So would you put that almost down to like the silicon lottery kind of thing? Like you talk about silicon lottery with CPUs, like it's all down to what bit of silicon that is being, like two transistors identical may have been taken from two different wafers of silicon and therefore will function very slightly differently, although they are built identical.
Yes, that's what your tolerances are essentially. So the gain of a transistor, even within the same model type of transistor, varies wildly. That's why the gain on transistors in data sheets is like the range is massive. Yeah, exactly. So what we do as designers is control those errors. And that emitter degeneration resistor that I mentioned before, that starts to control some of these non-linearities. It's like when you start putting negative feedback in an op-amp. The gain of an op-amp is like 100,000 to 10 million open loop gain. Whereas in transistors, you can achieve negative feedback just by adding a degeneration resistor. So you limit the gain and you start to control its response. It becomes a lot more linear. So you start to negate those issues with production. So what I've done now is I've started playing this, but there's no audio coming through. And that is because, this has gone fuzzy as well. I've not turned the amplifier on. I'm just going to attempt, will this, 1 second. Yeah, anyway. I'm going to get rid of the infinite averaging. You're going to have to say, hello, guys. And then this should refocus. That waveform that we saw a few lectures ago, where, you know, that crossover distortion, that's exactly what that is. Can you hear that that doesn't sound like a nice sine wave?
Yeah.
Can you tell?
Yeah.
It's got all that high frequency part to it. Well, when the harmonic distortion has got so much amplitude, then you can actually hear it with your own ears. And that's what that is.
And are all those extra harmonics, they're all caused by the crossover?
They're caused by this flat part.
Yeah.
So you wouldn't, you know, you wouldn't necessarily intuit that to create this flat part of the waveform, you'd add all of these sine waves together like that. But that's what you do. Because this is essentially telling you how many pure, you know, if you summed all those pure sine waves together, you'd come out with this waveform on the left-hand side. So, I think if I close this, it's not going to be as sensitive to my voice. It's a bit better, isn't it? Yeah. So I'm going to reduce this level and turn it off, because otherwise I'll blow my speakers, my headphones. And the next thing I'm going to try is I'm going to put those transistors in the feedback loop of the op amp this time. It's a lot better, isn't it? There's still a bunch of the same type of harmonic content, but it's the amplitude of it has been limited massively. And you can see that the waveform looks really nice and clean as well. Now, this is the beauty of FFTs and analysing it with this kind of, you know, at this level, because you can see things that you just would never be able to see before on an oscilloscope in, you know, that format. Also, bear in mind, the FFT is taking lots and lots and lots of these cycles, averaging it, and then extracting this really fine, minute data. If I... Do you remember on one of the things, it actually said, on a few weeks ago, the slide said, just watch out for this tiny little notch, because that's what the op amp... So the op amp's doing its darndest to correct this error, but it can't quite do it perfectly. And that is precisely. That little tiny little thing is causing all that spectral content. This, you can hear it if you put the headphones on, but you have to like really concentrate. So yeah. So next mode. I'm going to put it back into non-compensated, but now I'm going to pull these jumpers off, and we're going to go into class AB instead of just class B. So now the biasing, those diodes and the resistors are now going to start to come into play.
So AB we have diodes.
AB, if I can,
Just so I can see.
yes, I open this. In class B mode, you can pretend that the diodes are short circuits and the resistors aren't there. So class B is just the two transistors on their own as the output stage. Class,
AB is with all of them.
yes. This terminal block here, you put two jumpers on, you short out pins 1 and 2 and short out pins 3 and 4, which essentially remove these diodes, which essentially gets rid of the biasing entirely. So now we're in class AB, where we're now holding the bases of these transistors off a little bit by 1 p.m. junctions worth of voltage. Now, the spectral you can't really hear this. It's difficult to hear this distortion. The spectral content is a different shape because you've got this kind of like decaying slope of harmonics, but it's not perfect. Now, I think with better biasing, as in, you know, the stuff that I was talking about with the thermal runaway stuff, with better biasing and an emitter degeneration resistor, these transistors will act more linearly, meaning there'll be less harmonic content. That's what you mean. More linear, less harmonics. I also seem to remember that these performed a bit better when I was testing them at home. So I think through all of my thermal runaway testing, I might have damaged them slightly. But, however, we've got one more mode to test. And the last one is...
Those were different tests.
Yes, well done. And that will be after, yeah, exactly. Exactly. And then now, we've got something that looks like that. See again?
What did we add?
It's still in class AB, but I've now put the op amp in the feedback loop of the class AB output stage. So the op amp is now attempting to correct for the errors. You know how it managed to get rid of most of the class B garbage? When you give it when you feed it something a bit nicer, like a class AB stage, the op amp can really do its job. The higher the gain of the op amp, the better it'll correct this stuff. However, that is looking like a pretty nice THD plus N. A spectrum.
So there's three options, A, B, and AB.
Yes, but I've not tested class A.
Okay.
There's only A and AB on this one.
What you did was start off with B then?
B with no compensation. The compensation part is the bit that I've added onto this, which is bringing the feedback of the amplifier into the op amps loop.
Is that in our circuits?
Yeah.
It is, okay.
Yes. So you can choose whether to compensate for the output stage with the op amp or not. So you've got class A and class AB, either with compensation or not compensation.
So this is the full result now. We've got full compensation in AB.
Yes, exactly. So what I'm going to do is I'm going to unplug the oscilloscope. And I will put infinite averaging on. And then stop that. And I'm going to save that as overlay 3. So I've run this a few times, and dependent on, I don't know, it changes. So sometimes I've had initial distortions of like 0.0037, or what else did I get? Yeah, around that. So, but we started today, for some reason, it might be cold, it might be something, but we had an initial distortion of 0.0015, but now I've got 0.0051. So we've added 0.004% distortion using this amplifier. Bear in mind that the biasing isn't very good, and I've probably broken it a little bit as well due to the testing that I've done. So in reality, that distortion level, driving a full range load, so I'm driving the headphones as hard as they can go, it's actually really good performance.
How much? 0.0035%.
Yeah.
Nothing.
It's basically nothing. Yeah, it's imperceptible. You just can't hear it.
It's there. But
It's there. When you use this kind of sensitive measurements system and circuitry, it's there. And also, like I say, emitter degeneration will linearize the system a bit. And then when I say better biasing, I'll put a transistor on in a diode mode, but also you can use a potentiometer as well to add and remove a little bit, so you can actually set the bias, and you'll probably be able to see the effect of that on the output as well.
Just to put it in context, in terms of AC power that we get from our sockets, I think the national grid has said they will allow up to 3%.
Got you. Yeah. So I mean, we're in a number of orders of magnitude difference in that stage. So that's not looking too bad. So what I will do, so you can see them. That's the original graph. Let me just get rid of the spectrum, and this is ours. So there's more first harmonic content, but there's less higher frequency stuff. Yeah. Not bad, not bad. There's plenty of mistakes on there though. So what I will do now, just to finish off, is I will show you the frequency response. I think I can just... So this is obviously the one that you want to keep as flat as possible. Yeah, exactly. You can see it as it sweeps up and down. Yes, exactly.
That's quite interesting.
There's a lot of spectral data that you can see. When you start moving the amplitude on the edge of clipping, you get these really bizarre, I don't know what they are yet, but you get these really bizarre spectral lines that shoot up and down the waveform as it starts to clip. Really, but yeah, you can see the harmonics following the fundamental there. But we can sort of tell at this point that our frequency response is flat as a pancake as well. So if I put that compared against the original ran a couple of times, but you can see they're both nice and flat.
Yeah.
Yeah, yeah. Obviously, we're going through my headphone amp here, so the amplitude is slightly larger. I've obviously turned the gain up slightly on that. So, yeah, just want to see if it gets rid of those. All right, distorted. I'm going to stop that, and then we can jump back into here. In fact, actually, yeah. That's it. That's the last. That was the last slide. So, thank you very much for coming. It's been a pleasure. I hope you've learned a bit.
Change the devices and not use this package that you're talking about.
Yes, don't use the D2 package on the linear regulators. Make your own from the datasheet. It's a simple one to make. Yeah.
And anything else about the transistors, as in the thermal runaway, to compensate that?
Yes, I will. I'll send an email out to round off all the bits and pieces that we want to do for this.
You have to adjust it slightly, I imagine. Otherwise, we're going to have to do what you did with this compound or whatever you use.
Yeah, yeah, exactly. One thing that I thought that you could do, it's not the best way to do it. I wouldn't recommend it on a professional design. But what you could do, can you imagine if these diodes were actually perpendicular?
Yeah, just go straight up.
No, as in,
Board.
so no, imagine you rotate one of these diodes by 90 degrees, and then you put one pad here and one pad here, and the body of the diode would lay on top of the...
Oh, I see.
That's what I thought
Straight
would be the way
on
to
top
do
of
it.
the actual...
Yeah, through a hole on top of that sound.
Yeah, I don't know. I don't think it's a... I don't think it's a... I've never seen it done before, but that's potentially one way that we could do it, at least. You'd probably need to put a bit of thermal goop on it as well, a tiny bit.
Yeah.
Or maybe use one of those little thermal pads chopped up, just a little corner, so you can just squish it on. The more correct ways to do it is the emitter degeneration will limit thermal runaway. Using slightly larger package of devices would do it, because then they're not going to heat up as quick. And also,
Maybe through hole transistors.
you could use through-hole transistors, but you could also use surface mount, which has got a bit of a pad on the bottom,
Yeah.
and then maybe put one on one side and one on the other side of the board, and then put loads of vias. So you've via connected them together. You know what I mean? You could do that as well. But then, obviously, in the more correct version, you'd use these transistors as the diode and short out the collector and the base, and then you've got exactly the same. The effects follow each other. But yeah. So there you go.
We're sticking around for see blow it up.
Do you want to see the thermal runaway? Yeah?
Yeah, I'd love to.
Yeah?
Maybe
Okay.
not to destruction.
Yeah, no, I'll show you the effects. If you guys want to see it, you can do, but I know it's 20 past 10 now, so it just depends if you want. Yeah.
Thanks very much.
No worries, no problem at all. I'll send an email out with all the pertinent info in there about what I've discussed today.
Thanks a lot.
No problem. Right, thermal runaway. So what I'm going to do is I'm going to, firstly, you need to see how this actually happens. So I'm going to do that by showing the oscilloscope. The second thing is that I need to set up a specific frequency on here, and I'm going to turn the generator into left and right, so stereo mode. So I've got 2 plots for both channels. What I'm going to do on one channel, the left, well, I'll do it on the right one first. So I'm going to put a digital 0 in one channel, and I'm going to put a 1 kilohertz in the other. So that means I've only got a sine wave coming out of one of them. And I had to put the digital 0 on one of them because the jack shorts itself out to left and right as it goes in. So if I play this, it will all become clearer when you see it. Unplug that. I've not got on the right channel. Okay. Now, it's what you're seeing now is a signal on the right channel, but not on the left. I've got no signal coming through the left, and I'm just monitoring the signal on that on the oscilloscope using the.
So the bottom one is the right.
Yes. I'm going to clear that, and I'm going to turn our peak holds off because we're not interested in those anymore. Now, what happens is, you see how the sine wave shifted? Okay? Now, I'm not going to do it because it's going to hurt my fingers. Did you see how the wave clipped? You got half clipping. I'll show you again. So that's fine. The sine wave, as you can see, is nice and sort of centered on the 0 point. Okay? When I put this in, you'll see half of it clip. You'll hear that it sounds a bit crappy. And now, it's permanently offset. See that? These transistors are now roasting hot. So that's now, the transistor was clipping, it got hot itself, the bias didn't change, it kept getting hotter, and now there's a permanent DC offset in the output of the headphones. It gets a lot worse when you put it in the op amp. So what I'm going to do now, and this might actually damage them. So what I'm going to do is put the op amp in the feedback loop of the.
Sorry, what did you do to make them very hot?
As I was plugging the headphones into the jack,
Yeah.
the tip ring sleeve part of the jack shorted out the left and right channels, or it shorted the left channel with ground. I can't either. And what that did was it created a situation where half of the waveform was clipped.
Okay.
So it was, instead of seeing a load, the transistors saw a short circuit. That's the problem. They were seeing a short circuit for a short amount of
It
time.
was open circuit. It wasn't a load. It was no load. Yeah.
It was short.
Yeah.
It was just yeah, because as you plug that in, it shorts out. If there was no audio coming through, it wouldn't care because there's no voltage to go through. But as soon as you whack it on full volume, and then you put a headphone in, it short circuits the transistor momentarily. That causes the initial heat, and once the initial heat starts, the biasing situation comes into play, and then you get thermal runaway. Does that make sense?
Yeah, and then when you stop and redo it again, it goes back to normal.
And do you know why?
No.
Because I've turned the circuit off, the output transistor has had a chance to cool down, and then you turn it back on, and you're not in that thermal runaway situation anymore.
So that's why you turn it off and on again works.
Yeah, exactly. Exactly. So that was in class AB mode with the op amp not in the feedback loop, the output transistors not in the feedback loop, so uncompensated. I've now put it in compensated mode, and I'm going to monitor that channel, and I'm going to very tentatively put this on. Okay. Now I'm going to. Okay, so I've put that in, and it's maintained its center point this time, because the op amp's doing a good job of keeping it centered. However, if I proper give it some, oh, it's not doing it with this channel. So
Do you think it's now because you've got thermal compound on that?
I'm using the other transistors. I'm testing at the moment the left channel.
Yeah.
I'll show you what it does on the right channel afterwards. If I... Okay, we're lucky today. So there might be just enough thermal connection, or I'm not generating quite enough heat. But when I did this at home on the left channel, also the left channel transistors might be a bit more damaged. When I did that, it maintained, you know, like a fuck.
Thermal runaway.
Thermal runaway. Now, the problem with that was, it wasn't just a little bit of thermal runaway. That's headphone damaging thermal runaway.
No.
These will be okay, they're quite beefy. Yeah. That's what happens.
At least it works.
At least it worked, you saw it, yeah.
You're
Now,
recording this, right, Dan?
say again.
You're recording this, right?
Yeah. Well, I've got the audio. I've not got the camera because I'm using it this one. But I've got the screen. I'm recording the screen and the yes.
Yeah. You can go to Glenn. This is why I need a new set of headphones.
Yeah. Yeah. So that's what happens in the compensated mode. So it tries to do its best to maintain 0 point. So the op amp will continually move in one direction, which gets that transistor hotter and hotter and hotter and hotter. And at some point, it just goes, I can't do this anymore. And it just hits a rail and destroys your headphones. So what I'm going to do now is I'm going to use the other channel. I'm going to put 1 kilohertz, yeah, that's fine, on the left, and I'm going to put digital 0 on the right. I'm going to move the oscilloscope to the other channel, and I'm going to run. And then we can... So what mode am I in? I'm in class A, B... Oh, that's fine. Uncompensated. Now, on the other channel, it was very easy to get that to offset a little tiny bit. You know, I just plugged it in and it basically just went... Boop, a little bit of offset. So this time... It tried, you see it tried, but then it corrected itself because the diodes are now sitting on top of the transistors. So, and I'll just reduce the amplitude so you can see it's still good offset.
What's the difference between channel right and left?
Dan's thermal modification.
What?
Dan's thermal modification.
I'll show you a picture.
You know, where he's got all the diodes across the transistors and the grey hoop. That.
Okay.
So,
Okay, so you
Left.
said telling me
Right.
D4 and D3 are channel right and left, and the other one is channel
Yes.
D4 and D3 is left.
Okay.
D5, D6, and these two transistors is right.
Okay.
Yeah, so when these diodes are bonded to those transistors, it's hard to, you know, the thermal runaway situation doesn't happen. But I was panicking at home, like, how do I fix this before Friday? So again, that's the left channel. This one was the left, because this is the one that I've done the mod on. And then if I go to, if I change it, and we'll do the right channel again, just so you can see how easy it is to get that to happen on the other channel. Oh, hang on a minute. I'm in compensated, so I'm just going to move it back to uncompensated, so it's an equivalent test. See, it's just drifted away now already. Didn't have to try very hard to make that happen on that side. So that's that. That's the thermal.
Yeah, you have to see it to believe it.
Yeah. It's one of those. It's like, does this really?
Is it?
Yeah.
Is it real?
How bad is it?
Yeah.
I didn't. This is something that I sort of discovered this week as well. So it's like a lot of things I've found in electronics that you only really get a feel for the situation if you've experienced it and you've had to deal with it, and then that knowledge is just cemented into your mind from that point on. The trauma of it, exactly.
I'm convinced.
Yeah, good.
Yeah.
Good.
So-
Good.